Hello, everyone. Avinash. I'm a fixed-term assistant professor at Hiroshima University. Um, Today, I'm going to be talking about how do we estimate or constrain volumetric rates of transients. So this is through a work I did in collaboration with Linian from Caltech, using some data from ZTF. So just to give an overview, because I work on time domain astronomy, I mean, since this millennia, we have had quite a lot of surveys, starting from LOSS, Supernova Legacy Survey. We had PTF, IPTF, and then ZTF now, which is discovering a lot of transients. We've seen a lot of increasing science.
So, some of them are
associated with these, countless discoveries which happened in 2006, like one of them being Halloween transient, which was a nearby microlensing event, the CONCAM mystery object, which was detection of cosmic rays simultaneously by different observatories. The Perseus transient, one of the brightest supernova till date, 2006 GY. The M85 transient, which was an emerging member of the class of transients called LRN, luminous red novae right now. New class of GRVs, which was intermediate duration, but didn't really trigger another supernova, was not triggered by a supernova. And the Galaxy transient, which was the discovery of a star swallowed by a nuclear black hole called the tidal disruption event. So I think the focus of time domain is to understand the astrophysics of sources which show these cosmic dramatic variations. And the surveys which are upcoming, like the LSST, which will come up in a year or two, will discover an entirely new class of transients, because what we are seeing is what our current modern surveys are susceptible to, and
which are primarily governed by supernovae, gamma ray bursts, cataclysmic novae. You have kilonovae, which were
eruptive flares, ejective. You have luminous blue variables, X-ray binaries, eclipsing binaries, and also some kinematic transients, which is supposedly discovered a lot by the CTF survey. So to bring you to the motivation of my talk, why study rates of transients? Because you can track the evolution of the universe, track the star formation history, constrain progenitor channels for various kinds of transients, depending on which transient you're looking at. Explain the dust budget, because many types of supernovae, especially the interacting ones, are a major factor in producing dust in the universe. Also explain the overabundance of R process yield in the universe, because the budget is not currently explained by the rates of just supernova itself. And we have kilonovae countering in, but then the overabundance is still question. Compute delay time distribution in core collapse supernovae. So this is basically trying to understand when the formation of the progenitor happened and its final explosion, and how much of binarity plays a role in such cases. So in all, there are many transients which we miss, because the photometric discoveries allow us to, I think, as of today, we are discovering around 20,000 supernovae a year. But we will miss more in the LSST era, because
many of these transients are intrinsically very dim or get lost because of bad sky conditions. The survey cadence is,
for example, ZTF is 3 days. If there's a fast transient which has a cadence of 1 day or less, it could just vanish away like GRBs. And our detection and follow biases due to our own human vetting, because we humans are the ones who choose to follow these transients spectroscopically. And if you see the histogram of transients discovery rate, it has been going up since 2000 and currently sits at almost, I think I would say 20,000 supernovae. And with LSST, this is going to go up 2-folds to probably 10 to the power 6 transients per year. So just to open you to this new era, which will be in front of us through LSST, which will discover countless transients, we'll need to be aware, we'll need to be open to observations of peculiar transients, because those which are not really discovered right now would have a higher discovery rate with LSST, because it can go much deeper. But that will also require a lot of spectroscopic capabilities, especially in the southern hemisphere, because of the primary sky coverage of LSST. And if you look at this chart, it shows the rough transient discovery rates by LSST. So luminous supernovae, which are rare, very rare, I think are discovered at the
Zwicky Transient Facility, will go up to almost 20,000. So even the rarer transients right now will go up plenty folds with LSST. But we'll have to pick and choose what kind of transient.
So in all, I'll just describe my work with ZTF and follow-up of type 1 super luminous supernovae. So what is volumetric rate? Number of supernovae that explode within a given time span and a fixed co-moving volume that is based on the redshift you decide. And in order to work for, so I worked on type 1 super luminous supernovae. So we need to decide SED models which best describes these supernovae. And the best experiment mechanism for type 1 super luminous as of current date is the spin down of a magnetar. So we use this simulation tool called SimSurvey, which uses the survey schedule of ZTF, which contains the time, pointing, and filter of each exposure. Basically, the whole survey pointings throughout the first 2 years of ZTF. The transient model, as I just explained, we use the spin down of a magnetar. We encoded that model into a object-oriented program, which generates these SEDs from which you can compute photometry through ZTF filters. And it generates these in time series. So you can compute the supernova SED at any phase as you like. And a randomizer, which allows for sampling of these parameters from a distribution of what kind of parameter space this transient model comes from. Because transient model is just the evolution, because spin down of a parameter of a magnetar has magnetic field, periodicity, the time period. All that could be randomized through the randomizer. So just these are the survey pointings of ZTF over the first 2 years. The data which I used for this current work is almost like 250 nights.
Unique field of view every pointing. This is the magnetar source class which we generated using the model.
We use this to model our discovered superluminous supernovae 1. And yeah, we draw the input distribution from the randomizer, basically, from the spectroscopic follow-ups that ZTF discovered type 1 superluminous supernovae. So on the top, you can see the luminosity function we drew from the ZTF sample, which they collected over 2 years. On the bottom, you can see these two histograms, green and red. The green one is basically the input sample from all the superluminous supernovae which were discovered in the archives by these 4 papers. And then on the right, we have the red ones, which are discovered by the ZTF and followed up spectroscopically by the ZTF team. And they have some, you can see the similarities. The archival sample was more sensitive to the brighter type 1 superluminous supernovae, whereas the ZTF was more or less even. And that's because of the way the unbiased public survey works in ZTF. We followed the simulation. We placed, so how the simulation works is we place transients at redshift sampled from a distribution. And this redshift distribution is based on our redshift cutoff. Because we know that some of these superluminous supernovae can go up to -23. Our cutoff, we place it at around 0.4 based on the ZTF exposure times. And
simulation then draws an RA index from a uniform distribution on the celestial sphere. And this is again based on ZTF coverage. So ZTF can look up to, let's say, -25 degree in RA index, sorry.
Bit is chosen as the T naught of the explosion, and depending on the model SED forms between the uniform time distance. So I used data from 2018 to 2020. The T naught is chosen between that randomly, and this is based on a number of simulations you do, and this will normalize. The transient light curve will be then generated based on if the survey footprint, which is based on, again, ZTF's coverage of the celestial sphere and the survey depth. If the transition is good enough to be detected, then it will show up in our simulations. And then in the end, we filter the light curves with the criteria used for spectroscopic follow-up, because that was decided by the team which worked with ZTF. And the filtering criterion are mentioned here, and some of them are just filtering low signal to noise points, having a cutoff, which is 19.5 magnitude, where we can constantly say the ZTF points have a 5 sigma detection, checking whether these points have separations of at least 12 hours to make them their not just noise and are actual detections. Fourth is the magnetar model. If we have pre-maximum points or
this will pass our spectroscopic follow-up queue, and this will get triggered or put on spectroscopic follow-up queue. And 5 is filter any events which are below galactic latitude of 10 degrees in order to filter out high extinction supernovae, because they might have other issues to deal with. So we designed this code which automatically filters the simulated light curves. It designs these plots for each of these simulated transients. And you can see it determines first 3 sigma, first 5 sigma, maximum detection, last 3 sigma, and determines which transients were likely to be detected in our follow-up. And yeah, these are just a couple of examples. So we divided our sample into nodes. Yeah, thank you. From our sample, we divided the redshift bins into two, lower redshift sample and the higher redshift sample. The lower redshift is 0.06 to 0.2, and you can see the blue ones are the ones followed up by ZTF, and they completely are biased towards the low luminosity ones because those are supernovae are more likely to be discovered when you're at lower redshift.
Prior to our simulations, and you can see these are the discovered super luminous in our simulations and the variations with rise time on the right. And if you look at the histograms for the ZTF sample and the simulated supernovae, as you can see on the right, the apparent magnitude distribution pretty much matches, and the K statistics on the bottom right matches, and it matches at the rate of 5e, so almost 500 gigaparsec cube per year for the rate of low redshift sample from ZTF. For the high redshift sample, we again draw the distribution. So these are the ZTF sample which was discovered, and there you can see they're more distributed towards the right, towards the left, which are the brighter end of the type 1 superluminous sapling. And pretty much the distribution here is the same with respect to rise time. There's nothing different, and at a similar rate, you can see on the right, the apparent magnitude distribution matches what was discovered by the ZTF. So simulated light curves and the ZTF sample and the K statistics pretty much says that these are correlated. We try to check if there are any variations with respect to peak magnitude and on rise time. And if you see, if the supernovae are brighter on the left, they tend to pretty much filter out at the same rate. But if you go towards the fainter end of superluminous supernovae, they get filtered out a lot more. You can see the filtered ratio on this, right? 0.3 to 0.6. And if they are fainter, they get filtered out much likely just because they are fainter. And if you look at on the right side, the rise time, there's almost no variation, because if you look at the right axis, the filtered ratio is only goes on from 0.63 to 0.68. So there's like a 5% scatter, but the filtering does not depend on when the supernova is discovered or its rise time.
Public survey data from ZTF and spectroscopic follow-up can help constrain the rates of these type 1 superluminous or for any other transients which we are trying to look at. However, human bias in selecting such sample is non-trivial. So what I discovered with this work is that we had to take care of a lot of human biases which went into the follow-up of these transients, and removing them is very tricky in the in our analysis. So work is still underway to communicate with the team to collate on human reasoning, because there were many people who were involved with this spectroscopy follow-up, and to get that common factor which we could filter out was again tricky. So this is what we've been trying to deal with, and this technically may be difficult for any transient, given that we understand the physical understanding of its evolution. And just in brief, future with LSST, we could do similar systematic follow-up of transients discovered by an unbiased survey. We would probably need a smaller telescope which can do spectroscopy up to 19.5 magnitude for any kind of peculiar transients, and follow up during
associate will help us constrain these volumetric rates much better, and we will also be able to correct for spectroscopy completeness because we know our program through a computer-driven algorithm. And if any, we could also remove or log the human biases which trickle forward in these follow-up campaigns. Yeah, anyone interested in is welcome to collaborate on such a project with LSST. Thank you.